Hello student, good morning. I am Dr. Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing some terms based on electrochemistry. Actually I am reviewing the electrochemistry and that is actually fundamentals of electrochemistry I am discussing. Entire chapter I will discuss. Then many points already I have discussed, and last class I was discussing variation of molar conductivity with concentration for a strong electrolyte. And I have discussed just I started discussing variation of molecular conductivity with concentration for a strong electrolyte. Now further I am going to discuss variation of molar conductivity with concentration for a strong electrolyte is given by Debye-Huckel-Onsager equation, that is lambda m, that is equal to lambda m at infinite concentration minus b under root c, where b is a constant depending upon the nature of the solvent and the temperature, and standard lambda m is the molar conductivity at infinite dilution. Means standard lambda 0, that is for standard 0 script is written lambda m, then above the lambda just 0 subscript is written, that is a standard lambda, or you can tell that is called molar conductivity at infinite dilution. Molar conductivity at infinite dilution. This is actually Debye-Huckel-Onsager equation. Question is asked, that is the lambda m is equal to lambda m at infinite dilution minus b into under root c, where b is a constant depending upon the nature of the solvent and temperature, and lambda m at infinite dilution is the molecular conductivity, molar conductivity at infinite dilution. Okay, and just for a strong electrolyte and weak electrolyte, that if you will see the plot, then easily you can understand that how lambda m, that is the molar conductivity, varies with concentration, and means under root c, lambda m versus under root c. Then you can see a strong electrolyte is upside, means lambda m value, means molar conductivity value is very high in case of a strong electrolyte, and it varies slowly with under root c, means concentration, and this for weak electrolyte, now you can see lambda m value is less, very less, and it is also varying, and after that it is becoming constant with increase of root c value. Here c is concentration under root c. Then lambda m value is less, means molar conductivity value for weak electrolyte like acetic acid is very less. It decreases, and after that it becomes constant. And a strong electrolyte like KCl, its molar conductivity is very high, and it also vary with concentration, but variation is slow. After that also it becomes almost not full constant, almost constant, and then again slightly it will increase. Okay, by the graph you can understand. Now next term I am discussing, that is the molar conductivity of a strong electrolyte. Here you should understand, molar conductivity of a strong electrolyte increases with dilution. Because interionic attraction decreases with dilution. This you remember. Why molar conductivity is more for a strong electrolyte? Then its main reason is that molar conductivity of a strong electrolyte increases with dilution. Means if you put more solvent, means like water, then interatomic attraction decreases. Between the ions, attractive force will become less. That's why it will move fast. Molar conductivity of a strong electrolyte increases with dilution because interionic attraction decreases with dilution. A small deviation at a higher concentration are due to larger interionic attraction. Molar conductivity of a weak electrolyte increases with dilution because dissociation increases with dilution. This also you should remember. Question is asked. Molar conductivity of a weak electrolyte increases with dilution. Same reasoning. Because dissociation, first of all, if this weak electrolyte will dissociate more, that's why when it will dissociate more with dilution, then conductivity will be more. Then molar conductivity of weak electrolyte increases with dilution because dissociation increases with dilution. And next point you have to understand, molar conductivity at infinite dilution. That actually infinite dilution symbol is lambda m upside 0 subscript, or you can write lambda m and infinity sign also, sign you can give at the top, infinity sign. Sometimes it is written lambda m 0 script, means 0 concentration, and other way same things you can write lambda m and infinite sign you can give, infinity sign, lambda m, but top you can write lambda sign. Both have same meaning. That is the molecularity, molar conductivity at infinite dilution. Then molar conductivity at infinite dilution for a strong electrolyte can be found by extrapolation to the 0 concentration, but that of a big electrolyte cannot be found. Okay, in graph you can see, if you want this for a strong electrolyte, in graph you can see molar conductivity at infinite dilution for a strong electrolyte can be found by extrapolation. If you want molar conductivity at infinite dilution, some concrete value, exact value, then that can be found by extrapolation to 0 concentration. But in case of weak electrolyte, this is not found, cannot be found. Now next term, that is a Kolrask law. Kolrask law, what is the Kolrask law? It is very, very important term. Kolrask law states that equivalent conductivity of any electrolyte at infinite dilution is the sum of the equivalent conductivities of the cation and anion Again, I am telling you one more time. Equivalent conductivity of any electrolyte at infinite dilution is the sum of the equivalent conductivities of the cation and anion. That is, lambda sign EQ, shortcut E and Q means equivalent. Upside 0 script you can write. Then this equivalent conductivity is equal to now ionic conductivity. That is also just like reverse of Y. Also that is called this also lambda only. But that is called ionic conductivity. Ionic conductivity of cation at infinite dilution plus ionic conductivity of anion, both, sum of both cation and anion. Ionic conductivity at infinite dilution of cation and ionic conductivity of anion at infinite dilution. All things we are telling at infinite dilution. Equivalent conductivity at infinite dilution is equal to ionic conductivity at infinite dilution of cation plus equivalent conductivity of anion at infinite dilution. Means sum of ionic conductivity of cation and anion is equal to equivalent conductivity at infinite dilution. This is actually Kohlraas law. Or you can tell molar conductivity of an electrolyte at infinite dilution is the sum of ionic conductivities of the cation and anion, each multiplied by the number of ions present in one formula unit of the electrolyte. Suppose salt is AXBY, AX, like just like Na2SO4, then Na is in 2 number, SO4 is 1 number, and like that way Al2SO4 whole 3, then Al2 is in 2 number, that is the X, SO4 whole 3, that is the Y. That's why generally it is written AXBY this way. X represent number of A ion and Y represent number of Y ions. Hence you should multiply it, X with A and Y with B you should multiply, just to know the whole number, you can say number of ions. Then now you can write like this also, just like equivalent conductivity, you can write molar conductivity at infinite dilution. All symbols are same. Only in the place of EQ you write a small m, molar conductivity. Then molar conductivity at infinite dilution is equal to X into lambda A at infinite dilution. Just simply you have multiplied by X because A is in X number, AX for that purpose, plus now anion you have to write. Then anion is in Y number, then you multiplied by Y into B negative, A positive, B negative. A positive means cation, B negative means anion. Hence you add both number, total number of cation, plus total number of anion, you add, correct? But these are the actually ionic conductance of all cation plus ionic conductance of all anion at infinite dilution. Means power you have to write 0. Okay. Then this molar conductivity at infinite dilution is equal to X into lambda A plus Y into lambda B at infinite dilution. Both cation and anion should be at infinite dilution. This is the formula, and this formula actually is used in solving the numericals. Now other, you can say, some important application of Kohl's law I am telling. These formulas are used. Actually what I discussed now, two formula, that is for equivalent conductance at infinite dilution and equivalent this molar conductance at infinite dilution. Both had same type of formula. Then what is their use, application, now I am telling. First application, there are actually mainly three applications are there. Three applications. First application is in the calculation of molar conductivity at infinite dilution for weak electrolyte. This is the first application. Calculation of molar conductivity at infinite dilution for weak electrolyte. Weak electrolyte, because weak electrolyte is difficult to know what is actually molar conductivity at infinite dilution. It is very difficult. It will not, because it will not dissociate full. It will dissociate partially. But if you want to know the molar conductivity at infinite dilution, then in indirect way that value can be known. I will give the example. Now second application, in the calculation of degree of dissociation, and in third, it is used in the calculation of solubility of a sparingly soluble salt. Because sparingly soluble salt means it will not dissolve more, very less. As for example, silver chloride. Silver chloride, hardly few particles will dissolve, only few particles. Even water is more. And AgCl also you have added more, but it will not dissolve. Only few particles it will dissolve. That's why it is called a sparingly soluble salt. And for this sparingly soluble salt, what is actually its solubility product? That if you want to know, then this formula, this concept, Kohl's law, can be used. Then in three places it is used. Then now I will tell example. First example, that is in the calculation of molar conductivity at infinite dilution for weak electrolytes. Actually for a strong electrolyte not a problem, because it will dissociate maximum. A strong electrolyte dissociates maximum, and actually it also, if you will add more water, if you will dilute, then there also it will increase, but slightly it will increase. But here in weak electrolyte it will not dissociate too much. That's why with the help of Kohl's law, its molar conductivity can be calculated at infinite dilution. Then example I am telling you for acetic acid. Acetic acid is a weak electrolyte, CH3COOH. Then now here actually you want to know this molar conductivity of acetic acid, CH3COOH. Then in indirect way you can calculate. How? Then with use of three salt you can calculate you can say molar conductivity of acetic acid, weak, that is a weak electrolyte. Then how you will take consider, actually you have to consider three salt. You have to use three salt, but all should be a strong electrolyte. All three salt, with the help of this salt, you can use you can say acetic acid, or for any weak electrolyte, three strong electrolyte you have to consider. Okay. With the help of a strong you will know the molar conductivity of weak electrolyte. Okay, to know the weak electrolyte, you have to consider a strong electrolyte. In indirect way, theoretically you are calculating. But what you are considering, 3 salt, that is well known. That value you are knowing. That is experimental value. Then here how? Then by one example it will be clear. Acetic acid you want, CH3COOH. It's a molar conductivity you want to know. Then here 3 salt which you will use, that is the sodium acetate. Sodium acetate will give, because it is a strong electrolyte, then it will ionize, full ionization will be there, maximum. Then sodium acetate will give sodium ion and acetate ion. Sodium is plus, Na plus, and CH3COO minus, acetate ion. Then sodium acetate will give sodium ion and acetate ion. Acetate ion is negative, anion. Sodium is positive, cation. Now second and third salt you will use, just to which salt you require, that depends upon that which electrolyte molarity you want to know. Then here for acetic acid, then you have taken sodium acetate. Then now acetate ion you got. Through the sodium acetate you will get the acetate ion. But now for the acetic acid, H ion is also required. Then how will you get H ion? Then that you will take from HCl. HCl will provide you H ion. HCl will provide you H ion, because HCl again, HCl will ionize and it will provide you H ion plus Cl ion. Correct? Actually only these two are main two, only these are required. Third automatically I will tell you how it will come. Then here HCl will provide you H plus, Cl minus. Then now your problem is solved. Because H ion value you are getting. Acetate ion value also getting. Then acetate ion plus H ion. It will give you complete. If you add both, then CH3COO minus plus H plus. In the solution, if you will add sodium acetate and HCl, if you will add, then obviously you will get acetate ion and H ion. Means you got acetic acid. But what is the problem here? Now Na is also there, Cl is also there. Na plus or Cl minus is also there. Then in solution NaCl is also there. Then now to cancel this NaCl, because every cation and anion has a conductivity value. Every cation and anion have some fixed ionic conductance value. It is a fixed experimentally. Then now NaCl is created. Then just to neutralize this NaCl, in formula here you have to write minus NaCl. Lambda means this ionic conductivity of NaCl at infinite dilution, means NaCl value you have to minus it, because it is created, NaCl created. If you will not minus, then its value will be more. But you want only acetic acid. NaCl is extra there in solution. That's why you have to minus it. NaCl you have to minus it. Means ionic molar conductivity of NaCl you have to minus it at infinite dilution. All two values, three values what you will use, that is at infinite dilution. And these values are experimental value. It is known. It is known. Hence, if we will put these values, means sodium state value, molar conductivity value of sodium state plus molar conductivity value of HCl at infinite dilution and NaCl value, molar conductivity of NaCl value at infinite dilution, all infinite dilution, then NaCl, NaCl is going to be neutralized. Then what you will get? Only you will get CH3COO minus plus H plus. Only you will find in solution. Correct? Then theoretically you will get molar conductivity at infinite dilution of acetic acid. Now second application I am telling you, in the calculation of degree of dissociation, then that is actually alpha. Degree of dissociation is denoted by alpha. Then alpha is equal to what? Molar conductivity at concentration C, at concentration, given concentration, any concentration, molar conductivity at concentration C divided by molar conductivity at infinite dilution. This you remember formula, okay, expression, that alpha, that is the degree of dissociation is the ratio of 2. Just like you are getting 95% marks out of 100, 95. Then you know that at infinite degree, at infinite dilution, maximum conductivity will be there. Then out of that conductivity, how much conductivity was there at any concentration? Not at infinite dilution, any other concentration. Correct? Like a 0.5 m, 0.5 m, 0.25 m, correct? Any concentration. It should not be full. Full is 100%. You have to not consider. Always that will be less. That is a molarity, molar conductivity at concentration C, any concentration, m by 10, m by 20, m by 25, m by 50, but that should be less than m. Maximum, less than maximum. Then here alpha is the molar conductivity at concentration C divided by molar conductivity at infinite dilution. Or you can tell alpha is equal to lambda m at infinite dilution divided by alpha is equal to lambda m value at given concentration C divided by lambda m value at infinite dilution. Shortcut. Okay, lambda m at C concentration divided by lambda m at infinite concentration or infinite dilution. Correct? Lambda m value at infinite at concentration C. Lambda m value at concentration C divided by lambda m value at infinite dilution. Then now if these two values are known, if these two values are known, then alpha value you can calculate. Just like your percentage I told you, 95 divided by 100. Correct? Like that is here that is a percentage, but here you are telling alpha. Then if both value you are knowing, then alpha means how much degree of dissociation is there, how much it dissociated out of 100, or 1 you can tell out of 1 how much dissociated, 0.5, 0.75, 0.8, 0.2, 0.3, that you can calculate. Third application I am telling you, in the calculation of solubility of a sparingly soluble salt. Okay. Then actually, as the solution is saturated but infinitely dilute, solution, just to remember, as the solution is saturated means now further it will not dissolve. Any solution, solute must be little extra. If it will begin to settle, it means now it is fully saturated. Just like if suppose you can eat 4 bread, after that you can't eat. If for fifth one is given, you will tell no, you will deny. Like that way, if in any 1 liter or any you can say any volume, we can take half liter, 250 ml, 1 liter, and you are adding particular, just take a simple example, 1 liter water you have taken and salt you are adding. Then in the beginning it will dissolve. If you add small, it will dissolve. After that it will not dissolve. Even you will stir also, after stirring also, it will not dissolve. It means saturation is saturated. If you add extra, it will settle down. It will not dissolve. That is called saturated. Then here you have to consider that concept. As the solution is saturated but infinitely dilute, at that situation lambda m is equal to lambda m at infinite dilution. Both will become equal. Actually, both are same concentration. Same became same. Lambda m is one term, and lambda m at infinite dilution, that is another term. But at a saturated point, it means both are equal. When it is saturated, maximum, you got maximum value, that is at infinite dilution. Then you are talking about the m. Suppose m is maximum, then at that time both will be equal. Lambda m is equal to standard, or you can say zero concentration, or at infinite dilution m. What will be its actually value? Lambda m is equal to lambda m at infinite dilution. That you should know. This is in case of infinitely dilute. In case of infinitely dilute, lambda m is equal to lambda m at standard infinite dilution. Lambda m at infinite dilution. And molarity, that time will become solubility. Only that case, in the case of saturated solution, molarity is called solubility. Correct? This concept should be clear. In case of saturated, both are equal, molarity and solubility. Both are equal. Okay. Then here formula is there. Lambda m is equal to K into 1000 divided by molarity. That is actually molarity formula. Molarity formula. Lambda m, that is the molar conductivity. Molar conductivity now we are considering as a solubility. Then here molarity is just like a solubility, you remember. Then K into 1000 divided by molarity. You will tell why 1000, from where 1000 came. Then molarity is measured in liter, per liter. Correct? Per liter. Molarity is measured in liter, per liter. In 1 liter, what is the number of moles? Number of moles dissolved. Number of moles dissolved per liter. Then that is actually concentration. That is also concentration, molar concentration. number of moles dissolved in 1 liter. That is also can tell concentration. And molarity is actually what? That you are representing molarity in term of, you are representing concentration in terms of molarity. You can represent in many ways. In normality, in molarity, correct? Percentage also you are measuring, you know all the things. But here, molarity is measured in per liter. That is actually concentration. Then here actually you are just dividing K, dividing by concentration in real sense, concentration in terms of molarity per liter. Then molarity you are not knowing, maybe 2m, 3m, correct? Means per m you have to tell. That's why you have to divide by molarity. Then molarity is mole per 1000 liter. That's why 1000 will go up. 1000 will go up. Then K into 1000 divided by molarity. Correct? Then here you will solubility. That is, solubility is measured also as a moles per liter. Solubility is also moles per liter, and molarity is also moles per liter. Then only terminology you have to change. Then solubility, that is equal to K into 1000 divided by, now you can write lambda m at infinite dilution. Lambda m means molar conductivity at infinite dilution. Both are, in the beginning I told you, both are same. At saturated point, both values are same. Hence, in the place of molarity, now you are writing delta m at infinite dilution. Means delta m at zero concentration or infinite, whatever symbol you have to write, you can write. Then here solubility means moles per liter, how much dissolved, that you can calculate very easily. Then solubility is equal to K into 1000 divided by lambda m at infinite dilution. Okay. Now next point I am going to discuss, that is a electrochemical cell. Electrochemical cell. Okay. What is actually electrochemical cell? Then actually it is a two type of cell. Cell means just like consider, cell consists of mainly three things. Fourth things also you can tell. Main four things I am telling you. Main four parts of a cell. There two rods are used. That is also called metallic strip. That is called electrode. One electrode is called anode. Other electrode is called cathode. Two types of electrodes are there, anode and cathode. Both are metallic strip. Correct? Then what is the difference between anode and cathode? Then here you should understand that some electrodes, when you will dip in the solution having the same cation, as for example Zn rod or Zn strip, when you will dip in ZnSO4, then it will have natural tendency to lose the electron, and some electrodes have tendency like other metal, like for example copper. If you dip in copper sulfate solution, copper in copper sulfate, then it has natural tendency to gain the electron. Then those metal like Zn have tendency to lose the electron, that is consider as anode, correct? And this losing tendency is called potential. Tendency to lose the electron is called potential, and because this potential is developed due to the anode, then that is called anode potential. And same way, cathode, which has tendency to gain the electron, means their reduction will take place. Then that tendency is called actually potential, but there is a reduction. This potential developed due to the reduction. It has tendency to gain the electron. That's why it is called reduction potential. Then in cell, two electrodes will be there, anode and cathode. One has tendency to lose the electron, other has tendency to gain the electron. When both are dipped in a solution having the same solution, but they should have different container, means Zn in Zn separately, and copper in copper sulfate separately. And actually when both will be joined by one, you can say, conduct wire through ammeter or voltmeter, correct? Anode and cathode you have joined by a wire like a copper wire, any conducting material. Then through ammeter or voltmeter, then you will see that current is flowing, correct? Indicator will tell it, indicator will move, okay, it will move in some direction, that will take that current is flowing. Then here what you have seen, in a cell, one anode, one cathode is required, means electrodes are required first. Second, suitable electrolyte, copper sulfate I told you, or zinc sulfate, these are the electrolyte, correct? Electrolytes always will produce cation and anion, correct? Positive charge and a negative charge. Ion having positive charge is called cation, ion having negative charge is called anion. Then here any cell requires electrodes first, second electrolyte, correct? Electrodes means cathode and anode, and electrolyte. And this I told you. Next, third important point, first you will consider anode first, anode cathode, only you count one type, and electrolyte, that is second, and third is this conducting wire through ammeter. These are three important parts. And fourth one you can consider as that both solution, how will you make contact? Then there one salt bridge is used. Then this, by the use of salt bridge, both solution will make contact. Salt bridge will be like that, that will be saturated solution of KCl, sometimes ammonium sulfate also, correct? K2SO4 also. And both end, it is just like a U-tube. One will be dipped in the one solution, like a ZnSO4, and other will be dipped in the other solution like copper sulfate. Then their both end, it is just like a U-tube made up of, you can say, glass only, and both end will be closed by porous material, that you can tell like agar. It will allow only to pass the ions, not the water, not the solvent, only ion can pass through it. Then salt bridge is also one part of the cell. Then now actually this is of two types. First a type is called galvanic cell or voltaic cell. This is the one type, galvanic cell or voltaic cell. What I discussed example, that is of galvanic or voltaic, both are same, correct? This is the one type, galvanic cell or voltaic cell, one type. Second type is electrolytic cell. Actually, in first type, current is produced. Current is produced in galvanic or voltaic cell, what I discussed. In second type, current if you will provide, then chemical reaction will take place. First case was there, due to the chemical reaction current was produced. In the first case, galvanic cell or voltaic cell, volt it will produce. Current means volt it is producing in indirect way. Correct? And in second case, volt you will supply, then chemical reaction will take place. That is called electrolytic cell. Okay. Then there two simple way you can tell an electrochemical cell or you can tell galvanic cell or voltaic cell is a device used to convert chemical energy produced in a redox reaction. Redox means reduction and oxidation reaction into electrical energy. Correct? And other type also told you electrolytic cell. There by the use of electrical energy, chemical reaction can take place, redox reaction can take place. Now next point I am telling you, that is the a redox reaction. What is actually redox reaction? Redox means reduction plus oxidation. A redox reaction consists of two half reaction called oxidation half reaction and reduction half cell. Correct? One reaction is called oxidation half reaction. Same way reduction half reaction. Example I am telling you. That is a Zn. When Zn will oxidize, it will provide, Zn will convert to Zn plus 2 electron. Then this is oxidation. Zn is losing the electron. This is the oxidation process. Zn is equal to Zn2 plus 2 electron. This is called half cell reaction. And now copper, as a cathode, suppose copper is there, then copper was dipped in copper sulfate solution. Then there copper ion was there. Copper sulfate will produce copper ion plus sulfate ion. Then copper ion will take the electron. Zn will dissolve. It will give Zn ion plus 2 electron. That 2 electron will be taken by copper ion Cu2 plus 2 electron. It will convert to copper metal. Then this is the reduction. Gain of electron is called reduction. Then this is called again half cell reaction. But it is a reduction. Reduction reaction half cell. Oxidation reaction half cell. If you add both, then 2 electron will be cancelled. Add both left side, right side, what is remaining, that is the right. That complete reaction will be called net cell reaction. Net cell reaction means Zn plus copper ion, that is equal to Zn plus copper. Only this will remain. Zn plus Cu2 plus equal to Zn2 plus copper. Then this is called a net cell reaction. Okay. Then this I have discussed. Also I have discussed about the salt bridge. A salt bridge is a U-shaped tube containing concentrated solution of an inert electrolyte like KCl, KNO3, K2SO4, etc., or a solidified solution of such an electrolyte in agar or in gelatin. It must be dissolved in agar or in gelatin. Again I am telling you, a salt bridge is a U-shaped tube containing concentrated solution of an inert electrolyte like KCl, KNO3, K2SO4, etc., or solidified solution of such an electrolyte in agar and guillotine. What is actually role of a salt bridge? The function of the salt bridge is to complete the inner circuit by flow of ions and to maintain electrical neutrality in the solution of the half shell. Actually, you have seen that electron will pass through the wire, through ammeter or voltmeter. Then from the anode side, through wire, it will come to this cathode side, copper side. Then there will be flow of electron. Then flow of electron is called current. Flow of electron is called current. Then through cathode it will enter the, you can say, solution, copper sulfate. Then copper sulfate, that is a copper ion plus sulfate ion. Then this side, copper side, both ions are there, copper ion and sulfate ion. And this side, anode side, ZnSO4 is there. The Zn ion is there, means plus Zn plus is there, and this sulfate ion is there. Then what will happen? Then here movement of, in the solution through salt bridge, there will be movement of ion just to neutralize the charge. Then here in the first case, when Zn is coming to the ZnSO4, then Zn ion concentration will increase because Zn rod will dissolve and it will come to the solution. Then Zn ion will go to the solution and electron will go to the rod upper surface and it will pass through the conductor. Then Zn ion will be increased. Then Zn ion will increase. Then Zn ion alone, it can't be there. Already ZnSO4 was there. The Zn plus and minus, it was neutralized. But now extra Zn is coming. How will it neutralize? How will it neutralize? Only Zn. Already earlier ZnSO4 was there, that is neutralized. But now new Zn ion is coming. Zn plus, how will it neutralize? For that purpose, to neutralize this Zn plus, now sulfate ion from the copper side, cathode side, it will come. And then it will become, you can say again ZnSO4 will come, SO4 2 minus, and new Zn ion which dissolved. Now it will be neutralized. Then now why sulfate ion is coming this side? Then that reason I told you. And what happened in cathode side? Actually there also problem was there, reverse problem of first one. Here copper ion plus sulfate ion was there. Then copper ion was depositing there. Copper ion was depositing on the cathode and the cathode rod. Then sulfate ion was becoming alone. Then how alone? Any anion or cation will be not alone. Always it should be neutralized. You remember. Neither you can't get only anion or you can't get only cation. Always both you will get together. That's why oxidation reduction takes place simultaneously. That's why, because as soon as copper ion will take the electron coming from the anode side at cathode, then that copper ion will deposit there. Then sulfate ion will be free. Then that sulfate ion will alone, it can't be there. And here Zn plus is alone, their sulfate ion is alone. Hence both will come together. Sulfate ion will come towards the Zn, or which can move faster. There they will go and it will neutralize. Then here upside current was, electron was coming, means current was flowing. Then solution side, this was going, ion was moving. Hence complete circuit is completed. Complete circuit is completed. Correct? Then flow of ion is also called current. Flow of charge is also called flow of charge, anion, like cation, anion flow, anything. Then flow of ion is also called, flow of charge is also called current. Then now I have told these things. And Daniell cell, what is actually Daniell cell? Then this is also, I discussed voltaic cell or voltaic cell, I discussed, or galvanic cell. Then in the beginning, actually, Daniel cell was the first one. Now other cell which is working like Daniel cell, that is actually called voltaic cell. Voltaic cell or this galvanic cell. This is also just like a Daniel cell, In Daniel cell, what I give an example now, in Daniel cell, that anode and cathode is fixed. Anode is copper, anode is Zn and copper is cathode. Then anode Zn in ZnS4, copper in copper sulfate. If you are using only this anode and cathode, then that is example of Daniel cell. But other electrodes are also there, which can function as anode and cathode. Then that type of, you can say, cell, where other than copper and Zn, many other electrodes are there. And that time cell also will function like Daniel cell. Correct? That will also function as a Daniel cell. Then if you are using other type of anode and cathode other than copper and Zn, that time you can tell galvanic or voltaic. If you are using only copper and Zn, that time only you can tell Daniel. Okay. Then the cell based on the redox reaction Zn plus copper sulfate, and that will give ZnSO4 plus copper. That is called Daniel cell. Okay. Means Zn in ZnSO4 if you are using, copper in copper sulfate you are using. This is actually net cell. Zn plus copper sulfate. Zn plus copper sulfate, it will provide you Zn sulfate plus copper. Then this is actually called Daniel cell. What is actually difference between electrochemical cell and electrolytic cell? Then already I told you, electrochemical cell, electrochemical cell means now current will be produced. Chemical reaction will convert to electrical energy. Chemical energy convert to electrical energy. That is voltaic cell, what I told you. That is called electrochemical cell. Electro means galvanic and voltaic. In that, in galvanic and voltaic, electrical, due to the chemical energy, electrical energy will get, current will get. And in this case, electrolytic cell, that is you have to supply volt, then chemical reaction will take place. Okay. Then galvanic cell, sometimes also called electrochemical cell also. But actually both are coming under electrochemical. Better you keep single mind. Voltaic cell or galvanic cell is one type, and electrolytic cell is of another type. Both are together, it is called electrochemical cell. Then I have told you about the difference between both cell. And now electrochemical cell, how it is represented, that I will brief you today's last. How we will make a cell. Then in cell, what you have to, how you have to write? Then first you write anode. After that, you write cathode, and both should be separated by what? Salt bridge. That sign is double line. One side anode you write, double line you write, and then other side cathode. Anode, between anode and cathode, double line you write. That will tell about the separation, salt bridge. Then anode, how will you write? Then anode means oxidation reaction will take place. Then you should write like that. Anodic reaction you should write, half reaction. Means just like a Zn is converting to Zn ion. Then anode side you write Zn oblique Zn plus. Means Zn is converting into Zn ion. That you should write near the anode. Zn bar Zn plus. Correct? And Zn ion, Zn plus means ion concentration. That you write what is the concentration of zinc ion. You don't know any concentration, it may be there. You can write C1. Like same way cathode side, their reduction takes place. Means here you have seen copper ion Cu++ was converting to Cu metal. Then there you should write Cu++ oblique Cu, means reduction process. Anode side oxidation process you write, and this side reduction process. Then symbolic way you write just anode side Zn bar Zn++. Here copper ion Cu++ oblique copper. And what is the copper ion concentration? Now suppose copper concentration is some value is there, you write C2, you don't know. Then this is the representation of cell. Then anode side directly you write any other electrode also same way. That is example, just for understanding purpose, same example I am giving you. Zn is Zn bar Zn+, after that double line, and then Cu++ bar Cu, and concentration first side C1 anode side and cathode side C2. This is the representation. This is the representation of cell. Now I am stopping only here. Thank you.